All right, so this next section, I know you can see the heading there. It says conductivity measures ionization, but I just want to prepare you for this. It's not a big deal, but I just want to make sure you understand where I'm coming from here. This section is about looking at acids and understanding the idea that some acids are stronger than others. And it's really about what the definition of acid strength is. Okay, so in this particular slide here, what I've got is I've got obviously an experimental setup here where basically I've got two plates there and there, and those plates there are just basically copper plates, and what's happened is you've got a solution here of an acid. In this case it's hydrochloric acid, which is dissolved in that water, and it's split up into its ions there, and of course that would be H+ ions and chloride ions. So far so good. So it's these two electrodes here are connected to a battery, which is connected to a light here. And of course, if this solution here can conduct electricity, then electricity can flow from the battery through the light bulb and then back to the other terminal there. And of course, that light bulb will light up. So what? Well, bottom line is this. The amount of conductivity of this solution is dependent on the concentration of the ions in that solution, in this case hydrogen ions and chloride ions. Now when you do this experiment, if you put hydrochloric acid in water, or if you add HCl to water, and you do the experiment, what you see is that the light bulb is well and truly lit up here, indicating that HCl is for all intents and purposes completely ionized. It's all split up into H+ and Cl-. Now in this case down here we get a very different scenario. So in this case here, this is acetic acid here, and in this case when you put acetic acid in water and you conduct the same experiment, you still see a little bit of a glow on the light bulb, but certainly not as much as what you do with the HCl. And the conclusion that you come to there is that the acetic acid doesn't ionize very much. That is, it doesn't split up into H+ ions and very much at all. Indeed, you can say it another way, that the acetic acid is mostly still the original molecules, right? And there's very little ions present, that is H+ ions and acetate ions, whereas for the HCl, it's mostly ions and very little molecules. So in other words, just using something as simple as this can give you an idea of how significantly acids ionize in water, and that in fact is our definition of whether an acid is a strong or a weak acid. So if we look over here for HCl, you can see here that the light bulb is bright. You would therefore classify HCl as a strong acid, and you would infer that there is a significant proportion of the ionic species, that is H+ and Cl-, compared to the case where you've got acetic acid. There it is there, and in this case you can see that the light bulb is dim. You would therefore say that it is a weak acid, it's poorly ionized, and it mostly exists as this form, the molecular form, not the ionized form of H+ and acetate ions. Up here we've got water, and water is in fact a very pure water, is a very poor conductor of electricity, believe it or not, and you won't see any light at all. and therefore you would classify water as a very weak acid, if you want to look at it that way, and your inference is that most water in fact exists as H2O, which is indeed the case. Okay, so let's have a look at this table here as a little bit of a summary then. Okay, so if we've got, and it doesn't matter actually now, let's extend it from acids to both acids and bases. If there's a strong acid or a base, what would you expect? Well, the number of molecules present in the solution for a strong acid and a base would be few. That makes perfect sense because most of it is ionized. You would expect that most of it is in fact ions. You would expect the conductivity to be very high indeed, and what this is really telling you is that the bond strength, that is the way in which the counter ion is attached to that H plus, is pretty weak, and it's readily broken and given up. If you go over to the weak acids and bases, you will see here obviously the converse of that, where you would expect that most of a weak acid or a base is actually just present as molecules. There's only a very small amount that's present as ions. The conductivity would be poor, and you would expect then, or you would say that the bond strength, that is between the H plus and the counter ion for it, is very, very strong indeed and difficult to break. Okay, and I will just do this slide, and then we'll stop there for a natural break in the lecture. So in this case, I just want to point out, this is drawing from material that we'd covered last week to do with equilibria. Where we're headed with this, of course, is the idea that acids and bases in fact form some sort of equilibrium in solution, and that equilibrium is characterized by an equilibrium constant. So here's a classic example. We've got hydrofluoric acid, HF, and in this case it's going to obviously react with water, just like I showed you before in those previous equations. So this is the equivalent of HA plus H2O, and of course that H plus is donated to the water. You end up with hydronium ion, and you end up with obviously the leftover, which is the F minus. Now you can express that equilibrium with an equilibrium constant K, and as you learnt last week, that equilibrium constant is equal to the products over the reactants raised to their stoichiometric coefficients. So if I'm looking at this equation here, we've got the products are going to be hydronium ion, H3O plus, there it is, plus F minus, there it is. So there's the products. Obviously it's 1 to 1, so there's a 1 there and a 1 there, but of course you don't bother writing it. And the reactant, or the reactants, are hydrofluoric acid and water. So they go on the bottom. Now here's the little trick that people find a little bit confusing when they first start doing this. Water isn't written as one of the reactants, and the reason for that is basically for the dilute solutions that we're normally working with. The concentration of water is essentially a constant, and it's incorporated into the equilibrium value here, so it's left out. So we end up with this equation here. Okay, just to help you out here a little bit more, I've also written this equation down here in a little bit of a different fashion, but it ends up being the same kind of idea. I just want to again make sure that we're clear with the terminology here. And a couple of other things that I want to point out to you is that, again, as I stressed in the tutorials last week, we need to get a bit of a handle on what this K value means. If you're given a K value, I expect that you can sort of look at it and get an idea of what's actually happening. And what I did in Toots was I said to you that for the equilibrium constant where it's greater than 1, obviously products are generally favoured over reactants, and if it's less than 1, reactants are favoured over products. The other thing that we might as well get started on now is this idea, and that is that if we're reading the equation from left to right, which you are by convention, when you're talking about things, of course, these are the reactants, these are the products, but if I happen to be reading it from right to left, can you see that this thing here, this hydronium ion, can actually add a proton to the F minus, in which case this hydronium ion would be by definition an acid, and of course the F minus would be a base. Now there's nothing magical about this. The only reason we're reading it from left to right is that's the convention that we use so we can talk about reactants and products, but of course there's nothing to stop us from reading back in this direction here. Now if we go to the next slide, we will actually do this one. Yep. Sorry, this is the natural break here actually, it's not that previous slide. If we go to this next slide here, I just want to introduce this idea and flesh it out a little bit further. If we've got, for example, this particular equation here, if we're reading it, and we would be to start with from left to right, I hope you can see here that what's happening is that water, in this case, is actually acting as an acid with this base here, which is our old friend ammonia. Now, you can't actually see it just by looking at this side of the equation. You've got to look to the other side to see what's going on here. But I think you can see that that water has lost a proton there. There it is now, it's OH minus. And so therefore, by definition, that must be the acid. And if you look here, you can see this guy here has picked up a H plus. So this thing here must indeed be the base. Now that's reading it from left to right. If I happen to read it from right to left, you can see that if the reaction's going back in this direction, which it can of course, it's an equilibrium, then this proton ends up adding to here and forming water, in which case this is the base, and of course this has donated a proton, so this is the acid. Now, this brings us to the title of the slide. It says it's acids and bases and their conjugates. So you can see here that if something gives up a proton and forms something, that something is actually going to be a base when you're reading back in the other direction from right to left. And if something accepts a proton, then you can see that if it accepts a proton, it will end up being an acid, because it can then donate a proton back this way for the reaction going in the opposite direction. So this, when you're reading from, and of course you were always reading from left to right, you would refer to water as the acid, and you would refer to the bit that's left over as its conjugate base. Here you would refer to ammonia as the acid, and you would refer to ammonia as the base, and you would refer to this as its conjugate acid. So for every acid, when it acts, there's going to be a corresponding conjugate base, and for every base, when it does its thing, there will be a corresponding conjugate acid. Just a little bit on terminology. Where does this term conjugate come from? It comes from the Latin con, meaning together, and jugum, meaning yoke. So they're yoked together, and you can see that that's the case. It makes perfect sense that that's the case there. All right, I'm going to stop there, and then I will go on and look at water.